Welcome back. In this lesson, we're going to switch gears a little bit from our normal discussion of statics. In fact, this topic of section properties and their calculations could probably fall into a whole lot of different engineering disciplines. Most commonly in a university setting, section properties are covered beginning in physics and into your entry-level statics class. But the way that we define section properties is characteristics of a member that are used to define physical behaviors. Factors like the width and the depth and the cross-sectional area and those kind of things all have special meaning and are very important to us in our study of statics. Now, obviously some are fairly self-explanatory, but just to kind of construct the things that we need to know, I thought I'd kind of walk you through the process, and then that'll lead us into ultimately our moments of inertia calculations, which are important as we start getting into deformation responses that you'll uncover in mechanics and materials. So here's what we do. Okay, now there's a lot of things that section properties can be used for. We can use them predominantly, as we said, in the area of mechanics and materials, which will cover things like stress and strain and deflections. You could toss in buckling of columns into this. They all require some form of section property to be able to compute or to be able to work with those, to give them any physical meaning. Right now, one thing that we need to be a little bit leery of is kind of our terminology. We're going to use some terminology today from an engineering standpoint as opposed to a physics standpoint, and that will play a role predominantly when we get into the moments of inertia, because physics calls it one thing and then engineering calls it something else, but they basically mean the same thing, if that makes any sense. Okay. All right, so the first one that we do almost always is determine the centroid, okay? It's hands down, it's the most important of all of the other properties. They all build off of this guy, and this is kind of like you've heard of centroid maybe by some other term, a center of area or a center of mass or a center of gravity, all fall into this category of centroids. Now, in most engineering applications here on planet Earth, the mass and the gravity are located at the same point, and area is often at the same location as well, assuming based on some assumptions. But in a true physics sense, from a theoretical standpoint, these can all be different locations within the same object. All right. So for us, we're going to focus on the engineering centroid, okay? And this is called the center of area. And this has some very, very important meaning to us as engineers. All right. All of our calculations for the moments of inertia all focus on that location, that set of coordinates, okay? And in fact, as we get into statics, when we start talking about axial loads, the axial loads are assumed to act at that centroid, at that center of area location, or the center of force, okay? And so we're going to make sure that we kind of keep that in mind for all the calculations that we're going to do. Now, what I've done is I've set up an example for us to kind of look at as we move forward. Get my page is set up here. I set up an example, and we're going to kind of work our way through all of these different topics using this simple little object. Okay, so here's what we're going to do. We're going to take for us, and we're going to start off, and a lot of this, what we do with section properties involves setting up a coordinate system and then basically figuring out dimensions. So what we do is I've got a simple T-beam here that's 6 inches wide, a 3-inch flange, it has a 2-inch web width, and then it's 4 inches tall for the web, okay? The overall width is assumed that this is centered on the object, so it's 2 inches from the left and it's 2 inches from the right, and this thing is centered. Now, obviously, you could have physical objects that are not symmetric like this, but for the sake of what we're trying to show, I thought this would keep it fairly clear while also putting a little bit of rigor into what we're doing. All right, so everything that we do, normally when I'm working with section properties, I like to set my coordinate system at the lower left. Okay, and what that does is that if I define this point as 0, 0, then all of my coordinates to points within the object become positive values. Okay. Now, you don't have to. You could choose any point that you wanted because the centroid location is a reference, is a relative distance based on a reference location. So for us, what we're going to do is we're going to calculate the centroid, which is kind of like the balance point. If you were to think of this as a physical object that had some uniform weight associated with the area, this would be the point that you could basically balance it on the tip of your finger and it wouldn't fall over, okay? It'd be a single point. So it's kind of a balance or an average point. as we start to look at it in those senses. Okay, so the centroid then is that special point. Okay, we're going to call it centroid, and it has coordinates of x bar and y bar. Okay, and that's measured relative to whatever we choose as our origin. So it could be a point on the object, it could be a point at the lower left of the boundary, it could be out in the parking lot outside the building. Okay, as long as I know how far I am to all of these other points from that point, it's our relative dimension, so it doesn't matter what you choose as your reference. Okay, but I'm going to call my x bar and my y bar, I'm going to define those based on a 0, 0, 0 origin, wherever that may be. Okay, all right, so the formulas that we look for x bar and y bar look something like the following. That x bar is going to be equal to the sum of xi ai all over the sum of the ai. Okay, and that y bar is sum of yi ai over sum of ai. Okay, where I is all of the regions. Now this is the discrete formulation. There is an integral formulation for what we're doing, but again, you've probably seen this, so I kind of want to get through this fairly quickly and get on to the moments of inertia and some of the more important topics. But it is a good, useful review to kind of go through. All right, so all we do is basically we're going to take our T-beam region, and I'm going to split it into two pieces. All right, I'm going to call this as region 1. I'm going to call this as region 2. And so what we can do is the points that we need to know is I need to know relative to the object. And the way that I do this is once I've broken this up into regions that I can handle, and rectangles are pretty easy for us, I like to redraw the coordinate system, and then I draw the object that I'm looking at, okay, because there's some information that we need to be able to compute relative to this object in order to be able to do these calculations. All right, so again, here's my x positive axis, here's my y positive axis. I know the object is 6 inches wide, I know that it's 3 inches tall, and then I know that it's 4 inches to the bottom of the member or this particular area as measured from my origin. That's my origin there. Okay. The other piece of information that we need is where is the centroid of this region? Okay. Now, this is a fairly simple shape. It's a rectangle. We know that the rectangle locations are located at the middle of the area that we have happening here. Okay. It's not so easy to find for this guy. So that's why we like to break these things down, is I can work with something that I know, and then we can combine all of these through these two equations over here to find the location of the centroid of some irregular shape or some combined shape. Now, incidentally, I do need to point out that if this was a three-dimensional object, there would be a third equation that could show up with respect to the z-axis. But for us, we're just going to look at the two-dimensional scenario for this. Okay, all right, so the things I need to know know C1. So based on this coordinate system in this area, I know that C1 is going to be located at half of 6, 3 inches. I know that it's going to be located at 4 inches plus half of 3, or 5.5 inches. And that gets me the location of this point. Okay, and then, so I need that particular parameter. Okay, I also need the area that we're looking at that's associated with region 1, and that one's pretty easy. That's just 3 times 6, or 18 square inches. Okay, and then if I look at my formulas over here, I'm going to be taking the summation of all of the x-coordinate times the area for all of the regions located inside of this object. So my x-coordinate in this is that x1 value is going to be 3 inches. Okay, so I'm going to calculate x1a1 as 3 inches times 18, which is 54. And then do the same thing for the y direction. That's going to be the y coordinate, which we said was 5.5. And so that's 5.5 times 18, or 19, or 99 inches cubed. We'll get us those pieces. And then we just proceed to go from one piece to the next. And then we'll put it all together here in just a second. So let's try the other one. Region 2, this is the web, or the stem of that T that we had happening. Okay, and again, we're just going to draw this exactly the same way that we did before. Here's my origin. Okay, I know that the web is 4 inches tall. I know that it's 2 inches wide, and it's offset 2 inches from my origin. That was coming off of that original picture that we had up here. So that's all of that information being copied down. Okay, and then all we have to do is play the same game. All right, we're going to find the centroid of region 2, and so we know that that's going to be half of the height of this, so that's 2 inches from my origin. Okay, so that's my y coordinate, and then I know that it's going to be 2 inches plus half of 2, or 3 inches total, that gets me to the center of the region, again, as measured from the reference. The one thing to remember is that your reference at O has to be the same for all the pictures involved in this, otherwise your numbers don't work out. All right, and then likewise, we're going to do x2 times a2, so that's going to be my x of 3 inches multiplied by my 8's 24, and then my y2 is 2 times my 8, which is 16. And that gets us all the properties that we need to be able to calculate these regions. All right. All right, so then all we do is we basically plug and chug. Okay, so if I look at it, I can calculate my x bar coordinate of the centroid of the combined shape. So this is my region 1. and this is my region 2, and these are all the xi ai's, if you will. So my xi was 3, my ai was 18. That was that calculation we did on the previous page. And then this guy is 3 times 8, so all of that over then the sum of ai, well, that's just a fancy word for saying a total, right? Because I'm just going to sum up all the areas of the parts. That's the region, the shaded region in our picture. So that's 18 plus 8. So this 78 over 26 gives me 3 inches. And if we look back at the shape that we had here, I'm going to grab it again real quick. Okay, that point should be logical. It says that this thing is balanced because, again, this web and this guy are all, their centroids are all at 3 inches. So it's balanced along that 3-inch axis. It has equal area on the left side of the axis as it does on the right side of the axis. Okay, so that 3 inches is confirmed by the calculation that we just did. Okay, and then do the same thing for the yi's. Again, just plugging in real quick. 4 times 18 plus 2 times 8. That's, again, this is for number 1. Okay, and this is for number 2. Okay, and then I can do my A totals, and so no problems. And this number, if you do the math, ends up being 88 over 26, or a total of 3.38 inches. Okay. Which means then that my centroidal coordinates as measured from the origin are 3 inches in the x direction and 3.38 inches in the y direction. So again, if this was x and this was y and that's my centroid, that's all it's saying is we're saying that this dimension here is 3 inches, and I'm saying that this dimension here is 3.38, and that gets me to that balance point, to the center of area on us there. Okay, all right. So again, just about every section property calculation that you'll do in a mechanics, materials, or physics class starts off with some sort of calculation involving a center of mass or centroid. Okay. Now, we did a center of area, and that's evident by the formulas containing this area equation, right? But if you needed to do a center of mass, maybe I want to do x bar m, well, then I'm going to do the sum of the mi times xi all over the sum of the mi. It's the same thing, but now this is a mass-based calculation. So it's the lumped mass that you have times its positional coordinate. So it's very, very similar between those two basic equations. All right, the next one that you do, again, this one's pretty easy. It's just the total area, and in fact, we did that up in the denominator of this guy. Okay, so this will be a very handy one. And so basically we're saying that the sum of the area is basically the summation of A1 plus A2 plus however many areas that you have. For us, we're just going A1 to A2. So for our example, the area is then just 18 plus 8, 26 inches squared. There's A total. Okay, and this becomes a very important calculation in stress when we start calculating the stress on an object from a load, from an axial standpoint. Okay, all right. Now, on to what we really want to talk about and really get into, okay? And this is the moments of inertia, okay? And so in engineering, we call this the second moment of area. And when I show you the formula, it'll become pretty apparent why this is what we're calculating, okay? Engineers call the second moment of area the moment of inertia, okay? Physicists call the moment of inertia the mass moment of inertia. So it's a different formulation and a different construction. Now, under certain circumstances, they end up being the exact same value, but we need to be aware that there is a physics difference happening here. So we're going to be focusing on the second moment of area. Okay. And now what this is this is a section property of an object that is taken relative to the axes that pass through the object's centroid. So that x bar, y bar guy that we were playing with, and, you know, if it was three-dimensional z bar, that's the point where these axes are located, and that's the point where these calculations are based off of. So I can't do this moment of inertia without having that point. So this becomes, you know, you have to do the centroid calculation first. All right, so let's talk about kind of what a moment of inertia is. Okay, now moments of inertia are used in bending mechanics calculations, among other places. And what this is a inertia, if you remember from the physics definition, is a resistance to a change. Okay, you know, if you know, it's the idea coming out of Newton's laws that an object at rest stays at rest until something causes it to move. Well, it doesn't just instantaneously start to move. It tries to resist the load until finally it does indeed start to move. Okay, now the moment of inertia, as we said, is useful in bending calculations, right? So if I have a beam that's here, you know, then the arrangement of this moment of inertia determines how far this guy will deflect downward. Okay, if this is the elastic curve or the deflected shape due to some load P acting on the beam. Okay, now in statics, we don't worry about this because we assume delta was 0. But the reality is that it is never 0. And so when you get into your mechanics materials classes and your structural analysis classes, you'll be figuring out ways to calculate this delta. And on a beam problem, this guy is given by an I is in every single one of those formulas. Okay, all right, so here's kind of the formal definition of the way that it's set up. Okay, now there is a lot of different moments of inertia. We're going to focus about the centroidal moments of inertia predominantly, and most of the time that's the ones that you're worried about. There are some other cases that you'll need some of the others, but for what we're doing is if I have some arbitrary region, it's kind of this big blobby thing. It's affectionately called the space potato in a lot of textbooks for some reason. Okay, all I'm going to do is I'm going to basically do a computation that involves looking at some finite area that has a width of dx by dy. Okay, and so if I do the computation for calculating, locating my centroid here, we found that's located at x bar, y bar. Again, there's my origin, and that's the coordinates of the centroid. Then the inertia calculation that we're going to do is based relative to these axes. And so the x centroid is said to be the horizontal, well, we say horizontal, it's the axis coinciding with the x direction that passes through the centroid of us. Okay, and so the moment of inertia relative to the x-axis, this ix, is going to be the integration of the area of the distance y squared times that incremental area amount. Okay, so, and what we're going to do, so this integral over the area is really just basically a summation of all of the areas inside this bounded region. Okay, but it's going to be a y squared dA. So now you see why it's called the second moment of area. Here's my area, and then I'm multiplying it by a y squared. That's the second part. Okay, and so it's an area times the distance. That's kind of like a moment. Instead of forces, we're using areas. So that's why this calculation is called the second moment of area. The IY then is the moment of inertia about the y centroidal axis. Okay, and it uses x squared times dA. Okay, so those are the two major ones that we have. Now, there are a couple others in there, okay? There's one called the product moment of inertia that has some specific meaning. Okay, for sections that are not symmetric, IXY is not equal to 0, then we're going to do a product of it. And the way I always remember this one is that it's the integral over the area, and instead of where we had, y squared and x squared, now it's one of each. So it's xy dA, and we can do the calculations associated with it. Okay, now like I say, we'll show you some meaning of what IXY is here in a little bit. That's another one. Okay, but again, for most normal engineering structural bending problems where we have symmetric shapes, this guy doesn't really matter a lot, but at least this way you've heard of it, and we can kind of address that as we go. All right, one that does have a little bit of importance to us though is the polar moment of inertia. Okay, so if you remember your polar coordinates from calculus, that was always an r times some sort of theta. Okay, and so this is going to be a polar moment of area. And this is used in torsion calculation. So if I have a bar and I take it and I try to kind of twist it a little bit, okay, the stress that's felt inside of the bar as well as the amount that bar will deform is directly tied to the polar moment of inertia. Okay, this guy in most textbooks classically is called as a capital J. Okay, and it's set up in a very similar fashion. Okay, so now we've got our same space potato, if you will. Okay, I have my dA, which is still dx by dy. Okay, and then all we're doing is we're going from the centroid and we're calculating the radial distance from that point to the center of that area. Okay, and we're going to call that as r. And then everything else is the same. This is my x centroidal axis. We have our y centroidal axis as the vertical. Nothing else has changed. And so if we kind of go in and we look and we kind of compare the two pictures that we had here and here, remember that we said x was from horizontally from that axis to the center, and then it's y from the horizontal axis to the center. Okay, and now we're kind of changing it a little bit so that now it's r directly. Well, that kind of formed a triangle, if you will. This is a 90 degrees. Okay, we have an x, a y, and an r. And Pythagorean's theorem says r squared is equal to x squared plus y squared. Okay, all right. So the formula for a polar moment of inertia is, again, the integral over the area of r squared dA. So it's that r. So it's still a second moment of area, but it's now a polar coordinate. Well, if I do this little substitution and plug in r squared here, I get integral over a, x squared plus y squared dA, and then I can kind of split these integrals and do an x squared dA portion plus a y squared dA portion. And if you look, well, this guy is ix, and this guy is iy. So j is basically the summation of the two that we just calculated before, and oftentimes that's how I will tally him up. Okay, now for circular sections, there's a formula you can memorize, and we can talk about that in another lesson. But for most of the cases, when I compute all of these, I'm doing it with ix and iy. Okay, and so then j is just ix plus iy. Very, very simple, very, very straightforward. All right, so let's try one, just a very basic one for now. Okay, and so what we're going to look at is we're going to define a very, very basic rectangular shape. Okay, and this is one of the, when you get a little bit of experience under your belt, this is one that you'll have memorized. You use this one over and over, but I want to show you how it's calculated for us. Okay, so we're going to say this guy has a width of b. We're going to say it has a height of h. Its center or centroid. Now again, I may be choosing some coordinate system that's way out here, but I know that the centroid is located at h/2 from each of the edges. It's at the middle of the object. Okay, and then I know that relative to this point, that it's b/2 to the right and b/2 to the left from the y centroid. Okay, so we're going to define the y centroidal axis of this particular region. Okay. So if we apply what we've just worked at on this, I'm going to choose an arbitrary area. Here, I'm going to call that as dA, and we know that that area is dx times dy. Okay, I know that from the y centroidal axis to the middle of him, that's what we're calling as x, and from the x centroidal axis up to the middle of dA is what we're calling as y. And so we've got everything set up that we need to be able to do. So let's go through and let's try to see if we can figure out what ix is going to compute to. Okay, and so it's just basically a calculus problem at this point. I know that I can take ix is equal to the integral of a over the area of y squared dA. Okay, and so I know that I can take a regional integral and I can turn it into two linear integrals, because for a rectangle it's pretty easy that this line is horizontal, this line is horizontal, and this one is vertical, and this one is vertical. That it's pretty easy to define this region in terms of two linear integrals, if you will. All right, so I'm going to make a transformation, say dA is now equal to dx dy, put my y squared on here, and then I'm going to integrate from h/2 to minus h/2, because again, what I've done is I have set this guy as 0, 0, the center, and that's where my origin is acting at. So if I do that, it goes from, the y integral goes from positive h/2 to negative h/2, and that's important, so that's where my limits are here, and then it goes from positive b/2 to negative b/2 as my bounds in the other direction. And so now we just kind of go through our math. Okay, since this is an odd function, I can do positive and negatives directly. I don't have to split it up, if you remember all of your basic calculus rules, and I can go through and I can do my math, and I'll save you some of the exercise of what's going on. If you want to work through the math on your own, you can pause the video and kind of work through it, but as I do it, ix then becomes bh cubed over 12, if you do all of the math. Okay, and it's a fairly, not hard. It's a little lengthy, but not hard. And so a lot of times for rectangles, I just memorize that that guy is 1/12 about his own centroidal axis. All right, and then we can do the same thing for the y direction. Okay, except now iy is the integral of the area of x squared dA. Okay, and then same property. The only thing that's changed now is that instead of y squared, I have an x squared. Okay, and so when I do that, I can go through and do the math. And now iy is I wrote it down wrong. What do you know? Okay, got ahead of myself. Sorry about that. I had it right here. Okay, iy is now h times b cubed over 12. All right, for that direction. So you can see that the moment of inertia is different depending on which axis that you're going about. And what that does, that kind of sets us up for figuring out, that depending on deflections, the bigger the eye, the smaller the deflection. And so if you look at like your house, and you ever go look at like the floor beams in your house, that's the reason that, if this is a, a 2x10, okay, if that's the 2-inch dimension and the 10-inch dimension is the height, if all the loads are acting on this beam or acting down, I get a bigger I because I have a bigger h from the ix value. All right, and so what we've done is we basically played this game, that's x and that's y. All right, and so that's why if you want to control deflections, you turn the beam so that the deep direction is up and down, as opposed to doing it some other direction, where it would be a whole lot bigger deflection. Okay, so but that's the basics of how these calculations are basically performed for Ix and Iy. All right, so let's go look at the product moment real quick. Okay, so same process, same game. Okay, the only thing that changes now is that I swap x and y in for that first term, and if we run through the math and we go through it, as I look at this, I get into this integral of b over 2 minus b over 2x times this huge quantity. It turns out this guy ends up being equal to 0. Okay, and so the product moment has some special meaning. It can actually be a test to tell you if your shape is symmetric or doubly symmetric. All right, so for us, for this, it's a doubly symmetric shape because it has two axes of symmetry. It was symmetric about that axis as well as being symmetric about that axis. All right, so this is kind of a test for that. And so by it being equal to 0, I know that it has a symmetric shape. Okay, and that's kind of important when you get into some advanced mechanics kind of things, that for singly symmetric and doubly symmetric on this, Ixy is always 0, and your Ix and Iy, the centroidal moments of inertia, become the primary or the principal moments of inertia. All right, but if you get into a shape that looks something a little different, maybe it's an angle, okay, then it's a lot more complex because Ixy is no longer equal to 0, and you have to do something a little bit different when you get into those calculations. Okay, in an undergraduate education, almost exclusively you deal with symmetric and unsymmetric sections when you start doing those kind of calculations. But I just kind of, again, once you're kind of aware, maybe not necessarily knowing what to do with it when it's not 0, but at least now you know that there is a difference in the behaviors, and then when you get to class, your ears may perk up when you start covering that content. Okay, now there is one problem, okay, and we'll cover that in our next lesson. What do we do if our centroid axis doesn't line up with the centroid of our region? Okay, and that can happen in a shape such as our example here, okay, which is the one that we were just talking about. Okay, I had two rectangular regions, and if I go through, we went through and we found the centroidal location here, okay, and again, this was, if that's my x positive reference and this is my y positive reference and this is 0, 0 on here, then this guy is my y bar. That's the centroid of the combined shape, and then this guy here would be my x bar for the combined region. Okay, what happens is that if you go and you do your moment of inertia calculation like we just did earlier, I can handle finding the moment of inertia of this rectangle, right? It was taken about his own centroid. It's the centroid of the area that you're talking about. Okay, the problem is that centroid is not the same as the combined centroid of this combined T cross section. Okay, and likewise, the centroid of this web portion is below that location. Okay, so it's not at that location either. So I can't add these things together. I have to get them all into the same basic reference. And for us to do that, we have to make use of a more general approach that's called the Parallel Axis Theorem. And that will be the topic of discussion in our next video. Okay, so at this point, we'll go ahead and stop there. Hopefully you can kind of get a sense of some of the basic type of section properties. I know some of it was probably review, but hopefully you found it a little bit useful to help knock off some of the cobwebs. If you stick around for our next video, we'll actually go in and do a calculation for Parallel Axis Theorem and talk about some more of the details of how it works and what it's doing and do a little bit more advanced. We'll continue this example. So we'll go ahead and stop there for now. As always, if you'll leave us some comments or some feedback in the comments below about what we can do a little bit differently or what we can do better, make it more clear, and please let us know. Please be sure to like the video as it helps us out. And if you would, please subscribe to our channel. And otherwise, I will see you all momentarily in the next video. Thanks. Happy engineering.